Catenary curves. Perhaps you've heard of these curves. They are seen in engineering and also in physics. In mechanics, you sometimes see them. They have to do with strings and chains and things like that, making curves under the weight of gravity. They're quite interesting. And today I want to show you a really amazing property that they have, a geometrical analytical property, which is quite surprising and very beautiful. So the equation of a catenary, maybe you've seen this before, is A cosh x over A, like this. And the first thing you're going to ask is, what is this cosh? Well, it's one of the big three hyperbolic functions. Hyperbolic, as opposed to circular functions. Hyperbolic functions. So we have cosh, cos hyperbolic, sine hyperbolic, and tan hyperbolic. Those are the big three. And they're analogous to cosine, sine, and tangent. And you could ask, in what sense are they analogous? Well, they have very similar identities. They don't look like, the plots don't look anything like the circular functions, but the identities that they satisfy are very similar looking, very reminiscent of that. So let's look at the definitions of these things. Cos h, or cosh, that's e to the x plus e to the minus x over 2. And sine hx, that's e to the x plus minus e to the minus x over 2. And tan hx, that's, you divide sine h over cosh, and you get, something very similar, except no imaginaries, very similar to circular function, but no imaginary numbers in the exponents. There we go. That's tan h. And we can now have a look at what the plots of these three look like. So here we have all three of them. Cosh is the blue, and sine h is the green one, and tan h is the red one. You notice that tan h is bounded between plus and minus 1, but cosh is unbounded, and sine h is also unbounded. And we have some properties. Cosh minus x is cosh x, and so cosh is an even function, and sine hyperbolic of minus x is minus sine hyperbolic of x. So sine h is an odd function, and you can see that here, that cosh is symmetrical with respect to the y-axis, but sine h is anti-symmetrical with respect to the y-axis. We have even more identities. Cosh squared x minus sine hyperbolic squared x is 1. And this is very similar to the one that you really know well. Cos squared x plus sine squared x is 1. Well, this is the hyperbolic version of this. And similarly, we have these addition rules. Addition of angles also kind of works. Well, it's a little bit different, but it does work here. Hyperbolic sine of x plus or minus y is this. It's very much like the circular version. And we also have the same kind of thing, an analogous one for hyperbolic cosine. And it looks like this. And you might notice that these things are, in fact, a little bit easier to remember because the signs are more symmetrical than the usual trigonometry ones. Of course, there's one for tangent also. And you could probably guess that it looks like this. Hyperbolic tangent addition rule. So that's very interesting. Now, the most important one, the one that we are going to use, that we're going to need, is this one. Okay. But all of these expressions, all of these identities are very interesting. And I want to give you an exercise to do, a challenge. And it's to prove all of these. Prove these. And you say, well, how am I going to prove these things? Well, okay, it's try this. Okay, we have the definitions, cosh, sin h, tan h. We have the definitions for everything. It should be possible to use a lot of algebra and prove that these things are true, that the left-hand side here is equal to the right-hand side. So that's what you have to do. I think it's a very interesting exercise. I've done it in the past, and I think you should do it. It's very enlightening and good. So now that we know what cos h is, we know that it's a hyperbolic function. So now let's look at some catenary curves. Okay, so here's a whole bunch of them right here, and for different values of a. So we have, it's a cosh x over a for different values of a. Now the thing to remember, the thing to see here is that this point, let's call this point V. So V is the vertex of the curve. So it's the lowest point, and A happens to be exactly this distance. So A is the height of the vertex V. So this will actually help us to understand what's going on when we look at this beautiful catenary property. This is going to help us understand it a little bit better. So here A is 1.1. So when A is 1, I have my most basic catenary, y equals cosh x, the fundamental catenary. Okay, so that's very close to looking like this blue one over here. Now let me state what this amazing geometrical property is. I'm going to write it out neatly. And at first it'll seem a little bit incomprehensible, but don't panic. We will dissect the meaning of it very carefully and draw a figure, and everything will be clear. So this is the property that we're interested in. This is the thing. So P is any point on the catenary. So for example, I choose P here, any point, and the perpendicular projection of the ordinate of P onto the normal line through P is a constant equal to A. Okay, so this sounds a bit incomprehensible, but we need to sort of think about these things. The perpendicular projection, what's that? What is the ordinate of P? Well, we'll see that soon. What is the normal line through P? Well, I think you know what that is, but it helps to look at a picture. And it's a constant equal to A. So this projection is going to be an invariant. The length of this projection is going to be the same A as this here. Okay, now that might not seem so impressive in words, but when we look at an actual picture of this, it's going to be quite amazing. So let me get an illustration of this ready for you here. Okay, so this is a bit hard to imagine, but now that we have the figure, it's not so bad. So let's think about this. Here's my curve. The blue is the catenary. So the blue, here, let me use some color here. The blue is the catenary, the blue line here. This is the catenary. And the tangent is this line here, a tangent at P. So there's P. And the tangent's there. The normal is 90 degrees to the tangent. So here's the normal line. Normal. So here's the tangent. And there's the normal. Now, what is the ordinate? The ordinate is the segment from 0 to y0. So P has coordinates x0, y0. So the length of its y coordinate, that's the ordinate. So why don't we use the word y coordinate? Why do we say ordinate? Well, ordinate is kind of a classical analytic geometry terminology. So we want to keep using it. But also it means something a little bit different. Coordinate is just the number y0. But I think when we use the word ordinate of P, that means this segment here from O to y0. So that's the ordinate. So let's write that down. O, y0 is the ordinate. And so we want to project this ordinate. We're going to project it 90 degrees onto the normal line. And we get this gray segment here. And that will give this length, this thing S. So the length of this gray bar, that's S. Now we're saying here that S is invariant. That's what this is all about. S is invariant. So if I move P anywhere along this curve, let's say I put P here, or I put P here, or I put P anywhere, or even put P out here, it won't make a difference. The length of this projection is always going to be the same. Okay, now that's very interesting. So, all right, how are we going to do that? Well, we need to calculate this projection. Well, we know the length of the segment. It's y0. So we need to know the length of this projection. Okay, so this angle is phi. That's the angle of the tangent line. That's not hard to compute by calculus. So that's phi. This is 90 here. And this here is 90 minus phi. And if that's 90 minus phi, well, that's 90 minus phi here. That means that because this is 90, that means this is phi here. And so the projection of this segment onto this segment is just cosine. Okay? So S is y0 cosine phi. And there we go. So, we have figured it out. All right. So, okay, we have a lot more work to do, but, we are getting there. So what is cos phi? Cos phi, let's see if we can use some geometrical thinking here. Well, it's this here, this length here, okay, from A to P. All right, so PA, and divided by, oh no, it's not PA, that would be tangent if I'm going to divide this by this. So I want to divide TA divided by TP, yeah. So we just have to choose something careful, and okay, TA divided by TP. Let's see if that works. Okay, so TA is the adjacent and TP is the hypotenuse. So TA divided by TP, okay, that gives me cosine phi. Great. So that's good. And so now my job is to find what is TA and to find what is TP. Okay. So the tangent of phi can be computed by calculus. Tan phi is y prime at x0. And the derivative of cosh is actually sine h. So by the chain rule, I get a over a sine h x0 over a. Now, if you don't believe me, you can use the definition of cosh and you can differentiate it, the two exponentials, and then you'll see that this is true. All right. So that's another exercise that you can do, is you find the derivative of cosh, find this cosh, x, find the derivative of cosh x, and you'll see it's sine h. All right, so this is sine h x0 over a. But if we go back here and try to look carefully again, we see that tan, this is what I was thinking about over here. Tan phi, that's here, PA, that's y0 divided by this length here, TA. So this is y0 divided by TA. But we know y0 can be computed in terms of x0 because we know this formula for the catenary. So this is a cosh x0 over a divided by TA. And so what happens now? Well, we have an expression for TA. Let's write this neatly. TA equals what? So that I bring the sign here down to the bottom. So I have a cosh x0 over a divided by sine h x0 over a. And this, okay, finally for TA, this gives me a cotan hyperbolic x0 over a coth. All right, so this is a formula that we have derived for TA. This is good enough. We don't need to go further. This formula will suffice. Now, we need to find, okay, we did TA. Let's use some color. We did TA. Now I need to find TP. What is TP? Well, TP can be found using Pythagoras law. TP squared. TP is T to P. Okay, so that's TA squared plus, okay, so TA, and then the vertical is y0, so y0 squared. And I can substitute these things now. I have a squared coth squared x0 over a plus, now what is y0? Well, in terms of x0, I go up here. I use my formula again, and I know what is y0. I can compute that. Okay, so y0 is a squared. Okay, y0 squared is a squared cosh squared x0 over a. Okay, so now I want to show you a cool trick, which is we're going to factor out the coth. And how do we do that? Well, what I'm going to do is multiply this term here. Let's multiply this term by sine h squared x0 over a over sine h squared x0 over a. Okay, so if we do that, we get a squared coth squared x0 over a plus, okay, so if I look carefully here, this cosh squared and this sine h can combine together to give me cotan h. So this is a squared coth squared x0 over a times, and now I have this left over, sine h squared x0 over a. And now I can factor out the coth, factor out the a squared also. Coth squared x0 over a, and I have 1 plus sine h squared x0 over a. But way up ahead, before I suggested that you try proving the theorem, the identity cosh squared x minus sine h squared x is 1. So we know that that's true. Okay, that's provable. And this becomes a squared coth squared x0 over a times cosh squared x0 over a. Okay, so we have a more compact expression for TP, sorry, not TA. It's so easy to make a mistake. TP. Okay, so let's use some color here. Okay, great. And I have my two factors that I need to compute cosine. So finally, S is y0 times cosine phi. All right. And what is y0? So again, let's review for a second. This is S, this gray bar, the length of this gray bar. We're going to prove that it does not change. No matter what P is, it doesn't matter. This thing is not going to change. All right, so y0, we can use the formula a cosh x0 over a times, okay, now cosine phi is, let's not make a mistake. Cos phi is TA over TP. TA, the adjacent, over TP, the hypotenuse. Okay, TA over TP. TA over TP. So that's, maybe it could be a long expression. No, it's not so bad. A cosh x0 over a. TA is a coth x0 over a. And TP is a squared coth squared cosh squared x. Oh yeah, hold on. I have coth squared x0 over a cosh squared x0 over a. Okay, I need to square root this because, oh, I made a mistake here. This should be a square, TP squared. Okay, so I have to square root all of that. Okay. Just be patient, A cosh. Good things happen when we are patient. Times a coth x0 over a. You know, it never seems so hard when I'm doing it just, not with the camera or the microphone, and I'm just doodling it on paper. It all seems so easy to follow and easy to explain, and then comes actually doing it in a video, and it's quite a different story. Okay, x0 over a. Okay, I think we did it. Okay, so let's cancel some stuff out. This a and that a goes away. This coth and this coth goes away. This cosh and this cosh goes away. And look at what I have left. Finally, I have S is a. Amazing. Now, you can sort of see this because if I bring point P all the way down here, then the projection is going to be exactly the length of this height from 0 to the vertex. Remember the vertex? And this from 0 to the vertex, that length is A. Okay, as we talked about before, that length is A. Okay, so that's the fundamental one. So S is A here. But we proved that S is always A. It doesn't matter what, it doesn't depend on x0. So S is invariant. Now, you think to yourself, well, some of you have good imagination. You can imagine this thing swinging around, all right? And this projection sort of swinging around. You could sort of imagine, but it's hard to imagine that this remains constant. So let's see if I can draw more figures to show you that it does. So here I have two figures where P is in two different places. So I've got P down here and P is higher up over here in the second figure. Now notice my projection is the same length. So here it's S, okay? And this length S is the same as this length here, A, because we proved that S is A. We proved that. So it doesn't matter where I move it. It's very beautiful. I can move this thing around like, you know, you can even try to build a machine with strings and stuff and a catenary curve, and I can move this point around anywhere. And through the normal line, the projection of the normal line through P, the projection onto that normal line is always going to have the same length. Now, as far as I know, the catenary is the only curve that has this property, aside from, let's say, maybe trivial case of horizontal lines. Horizontal line has this property too. But it would be very interesting if you could find another curve that has a property like this, or something similar, maybe projection onto the tangent line of something. Or, well, you can invent your own concept, but take this as like a model and see if you can find other curves that have properties like this. Invariant properties like this. You can invent your own. It's very, very interesting. S is A. S is, let's write that again. Is a very amazing theorem. The length of that projection is a constant, A. So this was problem 1007. Well, it's based on problem 1007 from the fantastic book by Minorsky. Now, this is one of the best math books ever. And if you want a really good math book, get Minorsky. Minorsky is something like 2,400 problems. And you just start at the beginning and you do all the problems and you become really, really good at math, you know. So it's one of the best books that you could get in math. It's been, I think you can find it on Internet Archive. It's available because it's a pretty old book, but it's really almost unsurpassed. I really never leave home without Minorsky. All right, well, that's it for today. I hope you were as equally amazed by this invariant property as I was when I first saw it. And if you like this video, please click like, and of course subscribe to my subscribe to my channel. I'll be making many more videos. I feel like doing some calculus videos soon, so maybe do some of those. All right, and I will see you next time.